Okay. Welcome back to our class in algorithmic problem solving. I hope you guys had a great weekend. Today we're going to be talking about disjoint set union and about some of the problems that you could solve with it. So, suppose you have a problem. Let's say you have a bunch of people and they all need to be assigned to a team. And so you have a couple restrictions. For example, let's say person A and person B are friends. They really want to be on the same team. And now you want to know, given a certain set of restrictions, do these two people, like let's say person A or person C and person D, do these two people need to be assigned to the same team? Uh-oh. Wait, recording stop. You close it.
Oh. Next.
Recording in progress.
Okay. So let's proceed with a demonstration of how you might solve this problem. So can we get like about 10 to 12 volunteers to like stand up if you want to be a part of this?
Or no, we'll just do sitting down.
Sitting down?
I think we'll work with this.
Oh, okay. Okay.
All right. So, we're going to start with the warm up, but we'll need you guys to kind of pay attention to make sure this works. Also, this is an experiment. We haven't tried this before, but I have reasonable confidence. Okay. So, everybody is now on a team by yourself. And we're going to give you two instructions. First instruction is that two teams will merge. Second instruction will be, are you guys on the same team? And this is just the warm-up, so we'll do a couple of things to make sure everything's understandable. So, nice. So, this is like the core problem at the center of today's lecture, is like, you'll have a group of things, not necessarily like teams of people, but you can imagine like if we did a ton of these operations with 1 million people, it would start to get really complicated really fast. So, yeah. And as you saw right now, that was like 6 people to remember in your head. Do you remember who the 6 people are?
I don't know names, but yes.
Sure. Yes. So it's these 6 people here. But you can imagine that like once we get to like 20 people, or like in the programming problems it would be like 100,000. It's definitely not going to be possible. So instead, we're going to do something where you only have to remember one person. So this will be a second demonstration. So this will be like a similar setup here. So everybody still starts on a team by themselves, but now the instructions are the same. So like we're going to be merging teams, but now merging process is going to be a little bit different. So here, we'll make sure that like you don't have to remember anything except for one thing, which is like who you're pointing to. So as an example, let's start with here. So you two are now merged, but don't remember who's on your team. We'll just do like you now point Jared. So yeah, and now these are called like parent pointers in like algorithms, but we'll actually do pointing. So could you point here? So you can imagine like, let's say, I won't make you guys go through it, but like, let's say merge all of you guys together, and we had this super long chain going all the way around. And then to check out 2 leaders are the same, we'd have to like go through that entire chain of people and get to the leader, and then do the same thing for another person, and then check if those 2 leaders are the same. You can imagine that would take a really long time.
Okay. So let's talk about how we might go about implementing this kind of idea. So suppose we wanted to find the leader, or in this case it would be the root function. What we would do is we would initially set the parent of every node to be equal to itself. So if the parent of a node is yourself, then you can think of yourself as the leader of your component. And so as we keep going along the chain, the root of our node, or let's say I'm node X, the root of node X must be the same as the root of the parent of node X. And so we can recursively use this function over here to calculate what the root of that node is. And if we want to join two different nodes, all we need to do is if they're in a different component, then we can just set the parent of the root of one node to the root of the other node. So as kind of a basic demonstration of how this code might work, we can see, like, let's say you have these 8 nodes. Originally, they're all the roots of themselves, as you can see from the parent matrix, the parent array. But now you added an edge from 6 to 7. You merged 6 and 7, and so now the parent of 6 would be 7. And if we add another edge, let's say from 2 to 0, then then node 0, or then the parent of node 2 would now be node 0. So if we add another edge, then the parent of node 7 is node 8. And then if we add another edge, the parent of node 3 is node 0. If we add another edge, parent of node 8 is now node 1. And if we add another edge, the parent of node 1 is now node 0. And so if we, for example, if we wanted to find, okay, what is the root of node 6? Well, the root of node 6, we go to the parent and find the root of that. So we find root of node 7. And then to find root of node 7, we go to its parent and find its root. So we find the root of 8. And then we find the root of 1. And then we figure out that, oh, hey, our answer is 0. And so that means that the root of node 6 is 0. And so essentially what we've done is we've traversed along this chain and we've arrived at the conclusion that, oh, node 0 is our root. However, this might take a long time. So let's think of ways we might be able to optimize this.
All right. Well, we're actually there's 2 different ideas. Actually, there's many different ideas which speed up the process, but we'll go over like 2 popular ones. The first one is called path compression. And so for this one, we'll go back to the demonstration, but let's speed up a little bit. Let's say just we have a long chain over here. Let's say you're pointing to him, and then we have the same thing going on over here where it's like this. So yeah, and remember, like, these chains are just like slow down this entire process, right? Because like whenever we're like looking at his T, we have to go all the way down this long chain of pointing. So instead, now let's say we had another chain over here. So let's just go like 4 people this way. So now we have a long chain over here, a long chain over here. And now let's say we were to check if you 2 are in the same team, so the back of each chain. What we would normally do before is we would start at you and then go 1 parent pointer forward, and 1 parent pointer forward, and 1 parent pointer forward. That would take a really long time. And then we'd also have to do the same thing for you. And then like if we were to like ask the same question again, we'd have to do the exact same process. We have to start back at U2 and like go up these long chains. And then that's just like super long time. I guess the time complexity would be like O of n. So instead, what we do, like the first time we ask that question, you already know that your leader is now her, right? And so what you can do is now, instead of this long chain, everybody over here in the back 3 can now directly point to her. So we could also see that over here. So like the first time we go through, like we would have to follow along this chain, but then the second time, like you already know, like your top leader is her, right? So then you can just switch. Everybody switch to just point to her, right? All right. So now like the power of this is now like if we now ask the same question again. So are you on the same team? We don't have to travel up these long chains. We just go up one, and then done.
Yeah, so this is a pretty cool optimization where essentially we've stored what our root is and we're redirecting our root to our parent to be the root. So the idea here is we're doing a simple modification to our root function where after we find what the root of our parent is, we just instantly redirect the parent to the root so that if we have any queries on this node in the future, we've essentially short-circuited the chain, and we can very quickly be able to figure out what our parent is. So let's go to the graph from our previous example and say we wanted to find the root of node 7. So what we would do is we would go up and we would look for the root of node 8 as before. We'd go up again and look for the root of node 1 as before. And now, once we know that the answer to this is 0, now what can we do? Well, what we do is when we go back to node 8 to relay that information, we also reset the parent using this like parent of x equals to the root of parent of x. What we do is essentially we've redirected node 8 to directly point at node 0 rather than pointing in the chain. And similarly, when we go back to node 7 also points directly to node 0 rather than going along this large chain. And so what ends up happening is if we query node 7 again, node 7 would directly point to the root, and so our future queries on this node would become a lot faster. Does everyone understand how this one line can impact how our root function is able to find the root? This is clear for everyone? Okay, so now let's go through the second potential optimization that we can make. And let's let Richard take it away with our fourth live demonstration.
If you guys remember the second live demonstration, I was actually kind of forcing a decision there. So if you remember, let's see. So when you two guys merged over here, and then so when you're pointing to him, and then when you're pointing to her, there's actually a decision to be made here. So so let's say you weren't pointing at first. So actually this is not the example. Actually, don't put that here yet. So the idea here is when I merged you two guys, I said leader 1 points to leader 2, right? You two are the two leaders. But either one of you could be leader 1 and leader 2. You could have been leader 1 and he could have been leader 2. In which case you would have pointed at him. And which one is better, I guess? Would it be better for him to point this way or to point this way? Yeah. Do you want to say why?
Then you don't have to change it.
What do you mean? Oh, you mean later on so you're saying it would be better for her to point to him because later on then he wouldn't have to change Yeah. I guess right now we're doing without the path compression. So without the thing we said last demonstration. But so right now we're not gonna change to the parents. To the leader, yeah. But that's the good idea though. That's essentially the idea. So if he were to point to her, then later on, when we're going up the chain, you're gonna have to go 2 spaces up, right? And to avoid that, we could just have her point at him. And now later when we ask you who your leader is, you're only gonna have to go 1 up. And the idea here is this was a bigger group. And let's say I guess if we had this much larger group, so let's say you're pointing at him and then he's pointing up here. So now now it gets even worse if you were to point to her. Because now all the way back at the back of the chain, you'd have to go all the way up here. And now your distance is increased by 1. And then so if you were to point at her, your distance just increased by 1. You're still pointing at her. But your distance increased by 1, right? Because he used to be the leader, but now she's the leader. And now your distance also increased by 1, right? And then your distance increased by 1. That's a ton of distance increases, and that's really bad. But the alternative is just that if you are the leader and then you pointed at him, now you guys are all pretty much unchanged over here. And that's just much better. And the idea here is this was a larger group. and we want like the smaller group of just one person to point towards the larger group instead of the larger group into the smaller group. So yeah. So now like we can like modify the procedure. We don't actually have to do it, but I think this small example is enough. But now like we just make one modification, which is the smaller group leader points to the larger group leader. Except that there's one issue here. I guess does anyone kind of see what the problem is? I guess like we're kind of assuming something when we say the smaller group size leader to the larger group size leader. Oh yeah, so if they're the same size, I think then it just doesn't really matter. We can just have either one. But that's a good illustration, yeah.
In reverse it, so the larger group size leader points to the smaller group size leader?
Yeah, so we could do that, but then we end up in the situation we had earlier where we had like this really long chain of people. Yeah. Oh yeah. Yeah, exactly. So how do you know your size? So right here, how would you know like whether you're the larger leader or not? Yeah. So yeah, you just said you'd have to count like everybody who's leading up to it. But then that just defeats the entire purpose. Is like we wanted to make this fast, right? And then if you have to like count everybody behind you, that wouldn't work. Does anyone see how to solve the issue? And remember, you can only remember. Okay, we'll allow you to remember two things in your head now, instead of just one. But yeah, the issue is how do we keep track of your group size? Yeah.
I just wanted to confirm, so anyone in the team needs to know which is the smaller and the larger team member? Is that the objective?
Well, the objective is just like we need to figure out like who's pointing to who here. We have like a decision to make here, and ideally we just want to know whose group size is big. Like I guess like here in the back, you don't actually need to know your group size.
Say you can like use a mirror or something.
Yeah, it's not a trick. It's actually a way. Okay, I guess like what I just said was kind of a hint. So like you don't have to actually remember your group size because you're never going to be involved in any of the decisions that are made later. You're kind of fixed at pointing to who you're pointing at, and then same for you. So yeah, you three don't need to remember anything. That's other things. Oh, yeah. Yeah, so it would be nice if our group leader just knew the size of their group. But then, how can they know that? Like, how do we know that? How can they make sure that they always know the size of their group? Like we started off, everybody, you all know your group size. It's group size 1, and then we merged you 2. So now you know your group size is 2. But now, how do we continue from that? Oh, yeah.
You could add one each time you like join another person to the parent, so you can keep track.
Yeah, exactly. So now like when we merge you two, or I guess, okay, in this situation, these two were a group, and now we're merging him with him. So you were pointing to him, and you haven't started pointing yet. And how do we know like, so like, how much should he increase his group size by? Or, yeah.
Well, I think you could just take whatever the previous group size was.
Yeah. Exactly. So you know your group size is 1, you know your group size is 2, and so if we merge this way, now your group size is 3, yeah. So you had 1 and you add 2. And actually, if you were merging by size, it would actually go the other direction. So you have the larger group, right? So now you know your group size is 2 plus 1. Yeah, and that's the key idea is that only the leader needs to keep track of their sizes, and then when we're merging 2 leaders, they just need to like add up their two numbers, and then we get the total size. Yeah. Anybody guys have questions on that? Right.
Okay, so how might this look in terms of code? Well, as we mentioned before, every time we merge, we let the smaller tree point to the larger one. And so we keep the same root function as before, where we recursively keep going up the chain and finding the parent. But now here, what we need to do is not only do we need to keep track of the size of all of these trees, we also need to make sure we're merging in the right direction. So suppose we already knew the size of all of the trees, because at the beginning we already knew the size of all of the trees, right? So if we knew all of them, then we can just say that like if the size of the root of the root of y is bigger than the size of the root of x, you can just swap them. And then after that, we want to merge y into x. And so what ends up happening is what we need to do is we need to set the parent of y to be x. And then we also need to maintain the size of this new tree, which must be the sum of the two sizes. So in this case, we're incrementing the size of x by the size of y. And this allows us to keep track of the size of every tree while we merge. And so we don't actually ever need to recalculate the size of anything to be able to find the right merge. So it actually turns out this observation alone is good enough to reduce our complexity down to O of log n. Does anyone have any idea, like, why might this be true? Like, what might be going on here that allows us to reduce our complexity so much with such a simple observation? Does anyone have No? Okay, so essentially what's going on is, suppose we were to merge, or suppose we were to move up in our root function. So we go from x to its parent. And so what happens then is we notice that every time we move up, our size must actually at least double. Does anyone have an idea for why this might be true? No? Okay. So the idea is like, suppose your size originally was s, and we're going to merge x, the node x, with its parent. So at some point, in order for this edge to exist, it must have merged before. So let's say we have our tree of x, and it has size s. And we have a different tree somewhere. Let's say this is p, and it has some size, whatever, right? So now, when we merge, we must merge x into p, right? Because p is the parent. So we merge x into p, but what actually happens here? What must the size of p over here be? Yeah?
Greater or equal to s.
Yeah. So this size must be greater than or equal to s, right? Because here we had a size s, and because we're merging by size, every time we merge into the larger one. So this must have greater than or equal to s. So now when we update the new size of p, what must the new size of p be? Anyone? Yeah? Yeah, so it must be greater than or equal to 2s. And so now, essentially what's going on is, in our final tree, this is still true. This parent must still have bigger than or equal to 2s nodes inside it. And so every time we go up, so we go up 1, it goes up to 2s. We go up 2, we go up to 4s, and so on. And every time we go up, our size exponentially increases. So because we know the size of the root, well, that cannot be more than the number of nodes in total, which is n. So that means that we can only go up log base 2 of n times before we reach the root. And so that means the depth or the complexity of our root function must be at most log n. Does this make sense to everyone? Okay, So I'll actually briefly mention the complexity of the other observations that we made. So for example, remembering your entire team actually is O of n on average, but you don't need to figure out why that's the case. You just need to know it's slow, right? Parent pointers is also O of n per query. So this is not very good because you need to go up the chain every time. But it turns out path compression is actually O of log n per query on average, which is incredible because it is also such a simple observation. I didn't provide a proof because it's actually quite complicated to prove that this is the case. But it is log n, and union by size turns out also to be log n per query, which is really nice, which we proved on the previous slide. So if now, like, for example, you can use both path compression and union by size. Like union by size is just a simple modification on the join function, and path compression is a simple modification on the root function. So if you use actually both of them, it turns out your complexity now becomes the inverse Ackermann of n. And what is the inverse Ackermann? Well, it's a function that, the Ackermann function is a function that grows extremely, extremely quickly. It grows so quickly, in fact, that, for example, the Ackermann of 4,3, I believe, is still not known to this day. And I believe that number is actually Ackermann of 4,2. And like, it turns out if you took the number of atoms in the universe and took the inverse Ackermann of that quantity, the number you would get is approximately 4. So the inverse Ackermann can be kind of thought of as like a constant factor. Anyone have questions? Or okay. So now I'll talk about minimum spanning tree, and it's like one of the classic problems that you can solve with disjoint set union. So what is a minimum spanning tree? Well, suppose you had a graph with n nodes, and let's say for now, let's say the graph is always connected. So now you want to choose a subset of edges that forms a tree, and this is what we call a spanning tree because this set of edges that forms a tree covers every single, it spans, I guess, every single vertex of the graph. And so we can say that it's like a spanning tree for the graph. And so, for example, over here, we see that a spanning tree might consist of the node 5, the node 1, or the edge 5 to 1, the edge 4 to 1, the edge 1 to 2, the edge 2 to 3, the edge 2 to 6. And so what we want to do is we want to minimize the sum of the weights of all of these edges within our spanning tree. So does anyone have an idea how we might apply like disjoint set union to potentially solve this problem? Like any like rough ideas? So recall during our trees lecture that if you have two different connected components, and let's say the structure within those connected components are a tree, and you add an edge between the two connected components, this new connected component must still be a tree because it's acyclic and now it's connected, right? So potentially what we can do is maybe let's say that you can have like a bunch of teams. Let's say originally you haven't taken any edges, so you have n different teams, and now what you want to do is you want to somehow merge these teams in such a way that you never merge a component with itself, and you want to merge the minimum total cost of all possible merges. And so the idea here is, let's say we be extremely greedy. Let's just take the smallest edge that is still in the graph. And if it connects two different components, we know that that can contribute to our tree, so we can just take it and add it to the MST. But if it doesn't, then we already know that these two edges are connected and we'll never need this edge again. So we can just discard it. So what this might end up looking like is, for example, you have a graph, which is the same graph as on the last slide. And so if we take the smallest edge, which is the edge from 1 to 4, we know, well, since everything originally is in different teams, 1 to 4 would connect two things in different teams, and so we take it. So, for example, does anyone want to fill in like what our algorithm might do in the next step? Yeah?
Connect 1 and 2.
Yeah, so it would connect 1 and 2. And I guess, again, if we wanted to see the next step, it might try to connect 2 and 4, but then it'll realize, oh wait, 2 and 4 are already connected. Like my DSU is telling me we've already merged these two nodes, and so we're not going to add that, and instead we're going to go to the next edge, which in this case would be 2 to 3. And 2 to 3 is connected, and so what we would do is we would merge 2 and 3, and then we go to the next edge, which is 1 to 5. 1 to 5 is not connected yet, so we connect it, and then we go to this edge, 3 to 4. 3 to 4 is already connected, so we discard it, and then we go to 2 to 6, we add this edge, and we notice that, oh hey, we've already had the entire spanning tree. So will this spanning tree always be optimal? And it turns out the answer is actually yes. And the reason for this, we can see through like kind of a proof of contradiction. So suppose that we have an edge that, so suppose we have an MST. Let's denote the MST with the black and blue edges that are on the screen. And suppose that our algorithm, in fact, took an edge, the red edge between A and B when it wasn't supposed to. And so now, because it took this edge, we have a like MST that, or a spanning tree that isn't optimal. Well, if this were the case, what do we know about the nodes A and B when this red edge was added? Anyone? Yeah?
A and B aren't connected.
Yeah, A and B are disconnected. So that means that one of those blue edges must have had a greater weight because we haven't processed that edge yet, right? So one of those blue edges must have a greater weight than our red edge. So what we can say is like the maximum of the weights of the blue edges is bigger than our red edge. And so, for example, let's say that the fourth blue edge is that maximum blue edge. We can consider maybe swapping these two. So like now we take the red edge and don't take that like maximum blue edge. And so now because this red edge was taken and this blue edge is not taken, now what we see is that our weight of this like minimum spanning tree, or spanning tree, I guess, has decreased because that edge had bigger weight than the edge we just replaced it with, right? And if you look at this tree, it's still a spanning tree. We've cut an edge which separated the graph into two different connected components, but now we've added an edge that connects those two connected components back together. And so we actually have a spanning tree still, and because we've shown that the total weight of this new spanning tree is less than the total weight of the old spanning tree, we see that overall we've improved, or we showed that the original quote-unquote minimum spanning tree isn't actually the minimum spanning tree. And that proves by contradiction that this algorithm must produce a minimum spanning tree. Does that make sense to everyone? Any questions or? Okay, so now I'll hand it over to Bolland to do a live demonstration of how you might code a minimum spanning tree.
Okay, so I found just like a very simple template MST problem. So that problem is there's a town with, there are n cities and emeralds between them, and you have to repair the roads to connect all of the cities. Currently, all of the roads are destroyed, and each road has a reparation cost, and you want to find what is the minimum cost of repairing roads such that all cities are connected. So this is exactly the definition of a minimum spanning tree that Larry gave us earlier. So we should just implement that exact same code. Okay. How big is this? Big enough? Okay. So first I use fast input because I have learned that Python is slow, and I often have not a lot of fun when using Python for these problems. So let's look at the input specification for the problem. So the first line will just have two integers and an m, which is the number of cities and the number of roads. So we just read those in. Map int input dot split. Okay, and then so the way we will solve this is we will use Kruskal algorithm, which Larry just explained, where we will maintain an disjoint set and like try to merge the nodes, try to add the edges into the disjoint set in increasing order of weight. So maybe next we can read in the list of edges. So I usually like to zero index my graph, so I will just subtract 1 from A and B. And then I will want to sort all of these. However, I want to sort by the third element of the tuple. So in Python, there's like, you don't need a return here. You can make like a lambda that returns that makes the sort function use the third element of the tuple when sorting. And now we will code the actual disjoint set union. So we will have the parent array, which is just where like for each index I, we just make it point to itself initially. And then we will have the size array, which will be all ones, because initially everything is in a component by itself. And then we will have like our find function, which will return the root of the component node A is in. I think, let's say we can probably code it recursively. If A is pointing to itself, then we just return it. Otherwise, we know that the root we can get by doing a recursive call to find the root of the parent of A. Let's say we will do path compression. So then we update the parent of A, and then we return this value. Okay, and then maybe let's make a merge function as well, which will merge the components A and B belong to. And then maybe we also want to know which of the merges actually happened. So, okay, I guess I should maybe give an outline of the overall algorithm. Or maybe like Larry already somewhat explained it, but like every time we will iterate through the list of edges in increasing order of edge weight, and we will try to merge the two nodes corresponding to the edge. If we are able to merge them, then we include that edge in the solution, and otherwise we do not. And then we will also need to keep track of like how many merges we do, or like how many components we add, because the problem requires us to check whether like the entire thing is possible or not. So basically, if we do like n-1 merges, then it's possible to connect everything. but if we do less than n minus 1 merges, that just means the initial input graph that we were given is disconnected, so we cannot. So how I will actually define my function is I will return true if A and B were in separate components and a merge actually happened, and I will return false otherwise. False otherwise. So first I just find like the representative element of A and B, because that's just a lot easier to work with. And then if the representative element, like the roots are the same, in that case I return false, and otherwise I will actually do the merge and return true. So now I want to do merge by size. So I say that if the size of A is less than the size of B, I just swap A and B. So now after I've done that line, it's guaranteed that the size of A will be the one that's like greater. So in that case, I will be merging B into A. So that's what these two lines do. I update the size of A, and I update the parent of B to point to A. And then finally I return true, because in this case an actual merge happened. Okay, so now I will have a variable for the answer, and maybe a variable for the number of components, which is initially n, because initially nothing is merged. And then I will iterate through all of the edges, which I already sorted. Okay, actually, maybe let's make this a bit interactive. What do you guys think I should do next? What do I have to do for each edge? So in the MST algorithm, we are iterating through the edges in increasing order of weight, and then what do we try to do with each edge? Can someone give me like any kind of an answer, even like a high level one? Yes?
If you can merge the edge and merge it over.
Yes, exactly. So I will say, so I will call the merge function on A and B, and if it returns true, meaning that I can actually merge them, then I include this edge in the answer, which means that so first of all, I increase the answer by W, where W is the weight of the current edge, and I decrease the number of components by 1. So the number of components is like how many different like connected components there are in the graph. Initially everything starts out being disconnected, so I have n components and I decrease that by 1. And then what should I do at the end? Well, what else am I missing? Anyone? Okay, so at this point I have computed the MST, and now I basically just have to print the answer. So the one more thing I have to check is whether the number of components is correct or not. So if the number of components is 1, then that means everything is connected, so I just print the answer. Otherwise I print impossible, because that is what the problem asks me to do. Okay, so we can try running it on the sample input. Is it already clicked there? Where do I have to click?
I just reload on the top left.
Huh?
I just reload.
Oh, reload the page. Why does that matter? Okay, whatever. Oh, I already had the input pasted. Okay, I output 14. Now, I can't actually I have to upload a file to CSES, so I will try going to VJudge. Okay, whatever, I'm sure I can go to VJudge in this tab as well. Larry, are you logged in?
No.
Sad. Okay, fine. I will just.
You can just not. You can file.
I can just.
download.
Yeah, I can just. Download this as a file, and then submit it. Where's the file download? Okay, cool. I'm sure that's stored somewhere on this computer that I'll totally be able to find. Okay.
Publish of files. Publish of files.
I'm clicking on choose file. Nothing is coming up. Oh, you're not. Wait. Yes, you are logged in.
Regularly.
Is this like a Mac issue or like it comes up in a different place or something?
Yeah, probably something to do with presenting.
Wait, Larry, do you want to?
You know how to use this computer?
Well, I would imagine he owns it.
So where would it be? Downloads probably. What is it called? CSCS MST.
Yeah, top right.
Okay, where's the? Huh? Wait, where's the? Oh, here.
Wait, what did you? Oh, you clicked OK. Sure.
That was the
Fail. Oh my god. Wait, just. Okay. Submitting Python. Okay. I think this will get TLE. Oh, it gets AC. Okay, cool. Okay, and on the contest, I put a slightly different MST problem because it turns out Python is slow and just sorting the list already takes 0.6 seconds. Okay. Does anyone have any questions? No? Okay.